Okay, guys, so let's see. Yesterday we did finish with something that I call the Castigliano's theorem. So Castigliano's mentioned that to find the generalized deformation, you will take the partial derivative of the total potential energy with respect to the force. But what is something that I say was very important is that you needed to have what? Look at your notes. What needs to happen? So if you wanted to find the deformation at a point here, let's say Q sub I, you must have needed to have a force applied at the same location, even though it's not part of the problem. Let's say this was the problem here, okay? Let's say force P. All right. So let's do one example about that. Okay, so we're gonna, and then before that, we derive the expression for the strength energy when a structure is subjected to axial loading, bending, torsion, and shear. Okay, and each one of these loads has a specific equation or definition for the strain energy. Okay, so this example here is for a problem that we're going to say is statically determined. So what does that mean? That we should be able to solve it by just applying the equations of equilibrium, summation of forces equal to 0 and summation of moments equal to 0. Okay, so here we go with the problem. We have a simple truss structure. Okay, which is going to be pinned at this location over here. And then we're going to have a cable at this location. So let's see, we have some dimensions. This will be 2, 2, height is 2. I get this should be 2 meters. The cross-sectional area of each one of the roads will be 400 millimeters square. Is made out of structural steel with material property of 200 gigapascals. This should be meters over here. Okay, and we have a force of F equal 100 kilonewtons. So the question in this problem, and this would be point A, B, and C. So the problem is to determine the vertical deformation at point C. Okay, so we go from simple to more complicated. So this one will be statically determined, but right away, we need to determine the vertical deformation at point C. Do we have a force applied at point C? Do you see a force being applied at point C? No. So what do we need to do? We're going to have to apply a force at that location, no? Okay, so we can use Castigliano's theorem. So let's say over here, let me call this preliminary work. I like this blue. So I'm going to say no force at point C. Okay, so what we're going to do is assume this one has different words, dummy, but I like to call it virtual. Vertical force at point C, okay? And we're going to call that force Q. So basically, if we do that, we end up having to solve the problem. We're going to have here F equal to 100 kilonewtons. We're going to have here the Q force. Okay, this is the virtual force. All right. So basically, initially we had this problem to solve, but since we want to find the deformation at point C, we need to add the force Q over here. Okay. Okay, so this is a truss. Okay, truss structure. Generally, what do we assume about any structure that is made out of trusses? We have been doing that all the time. What would be the loading on each one of these members? It would just be axial, no? Okay, so you will say truss structure, each member is a one force member or two force member, okay, but depending on, so one force member, basically meaning that it can either be in tension slash compression. So each one of those members, let's say they are rods, this way they're going to be tension or compression, okay? Let's say I put it here in tension, or it could be just compression. So one thing here, okay? If they say here on this structure, there's a reason why this is a cable, but so this one is a cable. In other words, a cable can only be what? Tension or compression? Only be in tension. These rods could be tension or compression, no? Okay, but this one should only be tension. So if you pull down over here, with this member here, be tension or compression? Would be tension, no? You will pull. I forgot to put 1 point. This will be A, B, C, and this one is D. Now that I see. Okay, so let me put it here. A, B, C, and D. Okay, so from previous notes, you're gonna have to help me over here because I don't have them. But basically, we know that Q sub I will be equal to the partial derivative with respect to the Q sub I at the location, which will mean that Q sub C will be equal to the partial of the partial energy with respect to Q, which is located at point C. And now, what is the strain energy for the so over here, I mean, I don't remember what we derived, but this will give you
E squared over EJ.
For the integral,
Yeah, an integral for purely axial.
p squared over EA, and this would be here dx or ds, no?
Yeah, and then 1/2 at the front.
Okay. 1/2. Okay. So what happens here is that really, if you think about it, let's say P will be equal to Q. Okay. Let's say A is constant. Okay. We're gonna have that this over here, you can rewrite this as, if you take the derivative of, so let's say you write this partial of with respect to P, so will be what? Would be 1/2 P squared over EA ds. So you simplify this stuff, you have Q sub C will be equal to 1/2 will disappear, you will have P. Let's say each member will be of length, whatever length would be the member, the length of the element. PA over EA, partial of P. Let's keep over here Q. Sorry for that, it's just notation, but it will help. So this will give you just for one member. But if we need to do, so one member would be either rod AB, BC, or AC, or CD, okay? So it will give you just for one of them. And if we add them all together, we have here summation sign that basically replaces the integral sign. Okay, where here P, it's important to specify, will be the axial force on each rod or slash cable for this problem. Okay, so like always, step one, we're going to do a free body diagram, some type of figure. This will be like going back to statics, so a long time ago. So let's see, we have here the figure. This one over here. 2, 2, 2. We have the force here of F equal 100 kilonewtons. We have the force Q over here. So A, B, C, D. So if I do the free body diagram, this point A, we say that is simply supported. So that means how many reactions? You can have A sub X, A sub Y. Now, let's see, I have a good question here for you guys. I clearly say here that this problem is going to be statically determined, correct? So statically determined means that it can only be solved, that it can be solved using the equations of equilibrium. Summation of forces equal to 0, summation of moments equal to 0. So out of these two equations here, for a 2D problem, how many unknowns can you have? If you have a problem in 2D, how many equations do you have from the forces? How many? 2, X and Y, no? How many equations can you have from the moment equation? One, only the one coming in or out the board, no? So that means what is the total number of unknowns you can have? 3, okay? So what do you think here in this problem? We say we have unknown AX, AY. What happened if we had here another simply supported? This will give 2 reactions over here, no? Dx, dy. So the problem will become statically indeterminate, which is not a good sign. So why do we say this is a cable? Because then if we only have one reaction, and we know it needs to be in tension, so I'm going to do in tension, and we over here dx. Okay, on the cable. One, let me put here. Okay. All right, so step 2, using the equations of equilibrium, which are summation of forces equal to 0 and summation of moments equal to 0. We're first going to have the summation of forces on the x equal to 0. This will give us what? A x minus the x equal to 0. Let's call that equation 1. Then I'm going to do summation of forces on the y. Oops. Guys, here I did a mistake on the figure. What is it? These two are switched, no? X and Y. So be careful. I just realized this is AX, this is AY. Okay, so on the Y, we're going to have AY minus F minus the virtual force Q equal to 0. So we're going to have AY equal to F plus Q. So let me put a value. I should have put 100 for F. So AY will be equal to 100 plus Q. Okay, and let's say that will be our equation 2. So first unknown, AX. Minus dx equal to 0. Second one, AY equal to 100 plus Q. Third equilibrium equation will be to take the moment equation. When we take the moment equation, we always need to specify about which point we're taking in the moments. So we're going to say over here, we take the moments about point A. We also need to specify in which direction the moments would be positive, counterclockwise. So if we look at the figure, so let's see. So AX, AY go through point A, so they don't create any moment. Let's see the force Q. So Q, what is the horizontal force? So the arm will be 2. With that moment about point A, go clockwise or counterclockwise? We'll go clockwise, so that will be negative, no? The other direction. Now, what else can we have? We can have dx. So dx will go what? Clockwise or counterclockwise? Counterclockwise will be positive. So dx times 2. And finally, we have the 100. The 100, we make it go clockwise or counterclockwise. So we have minus 100 times, and the arm would be 4. And we have over here equal to 0. So we can solve over here for, so we'll have what? 2dx will be equals to 2q plus 400, or we will have that dx will be equal to q plus 200. And this will be our equation 3. Okay, so now that's it. Let's do a little summary over here. So we have, so summary. We need to find the expression for the axial forces. So we know that the force on the cable will be Q plus 200. So this will be the cable. Then what do we know? AX. So from equation 1, we will know what AX will be equal to DX, will be equal to Q plus 200. Okay, and then from equation 2, we know that AY is equal to 100 plus Q. Okay, so remember over here, in order to be able to apply this equation over here, what is P? P is the axial force on each one of the members. So we need to find what is the axial force on each one of these members. So let's see, from statics, what is the method that you use? So step 3, determine axial loads P. So what do we use? This is static. So a long time ago, using method of joints. So let's say we first go to joint A. Like always, procedure is what? Always do some type of figure, then apply the equation. So let's see, we have over here AX equal to Q plus 200. We have AY, which is equal to 100 plus Q. Then, let's see, I'm going to do that in blue. We're going to have here, let them do intention. This will be the force going through the member AC. So we're going to have over here P AC. So it will be the force in the member AC, and we need to do the same thing with the force in the member AB. I'm going to do over here. PAB. And since the distance here is Okay, because of the characteristics of this triangle, it's an isosceles triangle. We know that the angles over here would be (45). Okay, so in order to simplify the notation, you are aware that sine 45 will be equal to cosine 45, which is equal to square root of 2 over 2, or what is the same? 1 over square root of 2. So if we multiply this one over here by square root of 2 on the top and the bottom, you get 2 divided by 2 square root of 2, which will give you 1 over square root of 2. Okay, so over here now to find PAC and PAB. PAB only has one component on the x, correct? This one, PAC is going to have one component on the x and one component on the y. Okay, so in order to save some time, let's first solve then for PAC, because this is the only one that has one component on the y. So let's do summation of forces on the y. Again, this is statics. What do you have over here if you do summation of forces on the y? You're going to have 100 plus q, which is the AY, minus what? Minus the PAC. Would that be cosine or sine 45 on this one? This is statics, guys. What would be sine or cosine? We go to the opposite side, which is the one going up, so it would be sine 45. All this would be equal to 0. And we just say that sine 45 would be equal to what? Whatever. You can do square root of 2 over 2 over, or 1 over square root of 2. Let me do over here square root of 2 over 2. So here we're going to get that 100 plus q minus square root of 2 over 2 PAC equal to 0. This is going to give us that square root of 2 over 2 PAC equal to 100 plus q. Or from here, we're going to get PAC equal to, let's see, square root of 2. Sorry. PAC will be equal to 2 divided by square root of 2, 100 plus q. And if I multiply the top by 2 by square root of 2, so top and bottom by square root of 2, it will give you 2 square root of 2 divided by 2. This will gives what? Square root of 2 of 100 plus q. Say that again. Here what I do, I multiply top and bottom by square root of 2. Okay, so you get 2 square root of 2 divided by 2, no? Yep. Top and bottom by square root of 2. I mean, if you have any questions, stop me over here. So we have the expression now. Yes.
1 square to right for PAC.
No, if you do 2
I just can't tell what that number is.
square root of 2 will give you what? 2 square root of 2 divided by square root of 2 times square root of 2 will give you what?
Yeah, just square root 2. But
okay.
Okay, that's what I did. Okay.
Was that your question?
No, I was just I can't because you scratched the number. I couldn't see what the number.
Oh, this is 2.
Yeah.
Yeah, sorry. Okay, so I'm going to go to the next page to do the summation of forces along the x. All right, so now we do for summation of forces along x equal to 0. So we look at the figure. What do we get along X? We get X. We get Q plus 200, which is the AX. Minus PAB, which is now the one we need to find. Minus PAC cosine 45 equal to 0. So again, we say that the cosine 45 square root of 2 over 2. So let me just rewrite. So this will give us over here, I could rewrite this as PAB will be equal to what? Q plus 200 minus square root of 2 over 2 PAC. Okay, so we have PAB will be equal to Q plus 200 minus square root of 2 over 2, and we just find out what is P of AC. So what is P of AC will be square root of 2 of 100 plus Q. So now what happens? Square root of 2 times square root of 2 will be equal to 2. We cancel with the 2. So we get over here the axial force PAB will be equal to Q plus 200 minus 100 minus Q. So we are lucky, we'll get here PAB. Then would just be equal to 100. So basically, so far, what do you see? You find out that the axial force for the member PAC is in function of Q, but that the axial force for PAB is constant. Okay, so we need to do the same thing. So we did it for joint A, we need to do it for joint B, and then for joint C. All right, so now we go to joint B. So let's see, how did I do the previous one? The black, so it's for some notation. We have here point B. We're gonna have the F equal 100 kilonewtons, or 100, so we'll be using kilonewtons. Then we have here, I use the blue. So remember we said this member here is in tension, so it will be PAB. Over here, action, reaction. And now, so I'm at this point here, okay, so tension, I'm gonna do the same thing here in tension. I'm gonna assume it's in tension. I'm gonna over here, PBC. Let's see if I use the same color as before, this would be 45. Okay, as before, sine 45 equal cosine 45 equals square root of 2 over 2. And we do the same thing. So this time it doesn't matter because we know PAB. So we can do either first summation of forces on the X or summation of forces on the Y in order to find the only unknown, which is PBC. So you can either do summation of forces on the X or the Y. So let's do it on the X. So what would be the equation? Would be PAB plus PBC cosine 45 equal to 0. So again, remember cosine 45 will be square root of 2 over 2. So over here we'll have PAB will be equal to minus square root of 2 over 2 PBC. Sorry, we need to find PBC. What am I doing here? The other way around. So, all right, I should have done that differently. So PBC is going to be equal to minus 2 divided by square root of 2 PAB. And what is PAB? 100. So we're going to get PBC will be equal to what? Minus 2 over square root of 2 times 100. Or if we multiply top and bottom by square root of 2, what do we end up with? Minus 100 square root of 2. Okay, you can leave it on this form, it doesn't matter. Just I try to simplify as much as I can. Okay, so we are doing pretty good. We have the force on the axial member AB, BC. What we need to solve now, what is on CD? Do we have AC? No. Yeah, we have AC. What's the first one we found? Square root of 2 of 100 plus Q, no? So we need to find now in the member CD. That's the only one we have left. So 1, 2, 3, 4. Okay, here we go. All right, so now we go to joint C. We do the same thing. So we'll go here to point C. So C, let's see what we have. We know that because we need to find the deformation at that point, we're going to have the force Q. Then we have over here the axial force PBC that we just calculated. In tension, we have over here the force P AC that we calculated. Now we have the unknown over here that we know needs to be in tension. PCD or PDC, PCD, which is the one of the cable. Okay, and if you want, okay, I don't know how you want to do this, but if you do it this way, find that this angle here will be equal to this angle or the other angle. So basically the angles here will be 45 degrees. So I'm scared of doing here the equation. So all right, let's try to do it here. Okay, I don't want to go to the next page. So we do summation of forces. Let's do on the X equal to 0. So I'm going to write it a bit smaller. Okay. So what will this give us? This will give us PCD plus so remember PAC is this one over here. All right. Come on the axial force. So it will be PAC. I mean, it's 45. So it doesn't matter which one you take, but it will be cosine 45 with the picture we have minus PBC because it's going on the opposite direction. also will be cosine 45 equal to 0. So this will give PCD plus, let me do that in blue. What is PAC? PAC we calculated before to be equal to 100 to square root of 2 times 100 plus Q. Cosine 45 is what? Square root of 2 over 2 minus PBC, so will be minus times minus 100 square root of 2 square root of 2 over 2. All right, so here we're gonna get PCD. So square root of 2 times square root of 2 will be 2. So this 3 will cancel. It will be PCD plus 100 plus Q. And this one, if I multiply both top and bottom by square root of 2, what do you get? 2 divided by 2 square root of 2. So it will be 1 divided by square root of 2. So we'll give you plus 100 equal to 0. So finally, this will give us that PCD equal to, let's see, minus Q plus 200. Okay, so again, all this stuff is from all-time statics. So you see, you probably almost did not use the method of joins in statics, no? Probably. All right, but you see, it shows up on your last year class. All right, so join C. So let's do a little summary of the axial forces. Okay, so we're gonna do a summary, which is a table over here. So let's see, I like this blue, the way it writes. So I'm gonna keep writing in blue, 1, 2, 3, 4, 5. All right, so summary, and then I do the table in blue. Okay, give some space over here. So I'm gonna say here, I'm gonna call this one member or trust, it doesn't matter. I'm going to say here we have the members, what? AB, BC, AC, and CD. All right, we just calculated the value of the axial force on each one of these members. So let's see, we go to member AB. We had 100. BC minus 100 square root of 2. AC square root of 2. Q plus 100. And finally, the one we just did, minus, open parenthesis, Q plus 200. Okay. Now, I'm probably gonna write it down again somewhere over here, but if you remember, we have this equation right here. We need to apply this equation. So what is this equation here? We have Q sub C equal to the summation of the PL over EA partial of P partial of Q. Okay, so what we're gonna do, I'm gonna do it here so it becomes easier for us. I'm gonna look here at what is the term of the derivative of the axial load with respect to the virtual force Q that we had to apply at the location where we want to find the vertical deformation. So if you do the derivative of 100 with respect to Q, what would be the derivative? Derivative of 100 with respect to Q? 0. Derivative of minus 100 square root of 2 with respect to Q? 0. What about the one for AC? Square root of 2. And what will be the last one? -1. Okay. The other thing that we need over here on this equation is the length of each one of these members. So I put over here L. And I'm going to do a small figure here at the top. Sorry. Thank you. So this is 2, 2, A, B, C. Okay, so what would be the length of this element over here? No. Square root of what? A squared plus B squared equal to C squared, no? So it should be square root of 8, and square root of 8 is what? 2 square root of 2. Okay, so I could say, let's see, member AB is how long? Will be 4. Member BC will be 2 square root of 2. What will be this member over here? The same as the other one, no? So 2 square root of 2. And what is the length of the member CD? Will be 2. Perfect. Okay, so since we did step 1, step 2, step 3, step 4, now we do step 4. Generally, step 4 is what? Solve, no? We have been doing all the time. So solve, which in this case means calculate the vertical deformation at point C. Okay, so we're going to say over here, recalling, we have the equation here, Q sub I will be equal to the summation of PL over EA, partial of P, partial of Q sub I. Or in our case, this equation will be what? Q of C will be equal to summation. How many members do we have? 1, 2, 3, 4. So let's see, from 1 to 4. PL over EA, partial of P, partial Q. Okay, I'm not going to start putting I's all over the place because it will be a nightmare. but this will become what? I could simplify this as Q over C, 1 over EA, because these two will be constant. Summation 1 to 4 PL times partial P partial Q. Okay, so is that if I do this now, this calculation, I'm going to factor 1 over EA. I'm going to apply this part of the equation for each one of the members. So what can I have? I can have PAB times LAB times partial PAB with respect to Q plus PBC, LBC, partial of PBC with respect to Q, plus PAC, LAC, partial PAC with respect to Q, and finally, plus PCD, LCD, partial PCD with respect to Q. Okay, so I'll give you 30 seconds here rest. A little bit. And now let's look at this term. So what will be partial of, if you look at the table here, what will be partial of PAB with respect to Q?
0.
So this term here is 0. What about PBC? 0. PAC, this one will be equal to what? Square root of 2. And the PCD will be equal to what? -1. Okay, and I know LAB is equal to what?
4.
4. Okay, but this will be 0 anyway, so zeros this time will be 0, 0. Let's look at this one. LAC will be equal to what? 2 square root of 2. LCD will be equal to 2. Okay, so we can go and substitute. And we know what, maybe let's do this in 2 steps, okay? So this will give us what? 1 over EA. So this would be 0. So let me write over here if you want. 0 plus 0 plus PAC times what? 2 square root of 2 times square root of 2,
Which just means it's
yeah, plus PCD times
2 times.
times 2 times -1. So I'm going to get 1 over EA. Next, what is PAC? What do we say was PAC? We should have it over here. It would be square root of 2 times Q plus 100 times what? Can I do 2 times 2? times 4, all right, plus PCD. What is PCD? Is
Plus 200 is
minus Q, maybe let me do here brackets, minus Q times, sorry. All right. Sorry for that. Plus minus Q plus 200 times -2. I wanted to do everything in one page, but I won't be able to make it. Sorry for that. So I'm going to rewrite this line over here because since I did a little bit of scratching over here, and that way we start here from the top. 1 over EA will be equal to square root of 2 Q plus 100 times 4 plus minus Q plus 200 times -2. Okay, so let's do the middle step over here. This is going to give us 1 over EA equal to what? Let's say 4 square root of 2 of Q plus 100 plus 2 times Q plus 200. Or I'm going to say here, or at the end, I could say Q sub C would be equal to 1 over EA. Okay, I'm not going to do more algebra. It's enough. 4 square root of 2 Q plus 100 plus 2 times Q plus 200. Okay, so now what is Q? Do you remember what is Q from the beginning of the problem? What did we say Q was? A virtual force, and basically yesterday I explained. So does that force really exist? No, it's just there to do the calculations, no? So really at the end, what we need to do is just say, okay, that virtual force really is not acting, so we can now say that it will be equal to 0. So let me write this down. So recalling that Q is a virtual force okay, now we can say that the vertical deformation at point C is obtained by, let's say, setting the force Q equal to 0. Okay, so what would that mean? We'll get Q sub C will be equal to 1 over EA times 4 square root of 2 times 100 plus 400. Again, I like the blue. So, or I can simplify this expression, say it will be, let's see, 4 times 100 would be 400. So let's say we factor out by 400 over EA times what? Square root of 2 plus 1. Okay, so a lot of calculations, but at the end, the expression is not that complicated, no? Okay, so let us do now the numerical application. All right, so here we go. So E, was it given at the beginning? Yeah, E from the first page is 200 gigapascals. So this will be 210 to the 9 pascals. Then we have A is 400 millimeter square. So how many meters square would that be? Don't wait for the answer. I'm not going to write down until you give me the answer. 400 times what? What is the relation between 1 meter and 1 millimeter?
1,000 milliliters.
Okay, so basically 1 millimeter would be 0.0001, 10 to the minus 3, no? So now it's square. So what do you need to do? You need to do the 10 to the minus 3 square, no? So what would that be? 10 to the minus 6 square. Okay? All right, so at the end, we will get over here. Q sub C will be equal to 400 divided by what? 200, 10 to the 9 times 400, 10 to the minus 6 times square root of 2 over 2. So if we do the calculation, this gives you Q sub C equal to 12.07 10 to the minus 3 meters. Or we could say that Q sub C would be approximately 12.1 millimeters. Okay, so really, you see what we have done today is a problem from statics But in static, you never had to find deformations. You only needed to find forces, no?
Mhm.
But you see how much more work is to find the deformation. Okay, so,
If we were to choose just any other different point. It's just-
okay, that's a question. So let me ask you a question. I mean, go ahead.
I was saying, if we choose any other point, even with the force, is there an easier way to go about doing it, or if you still have to do the quote unquote virtual force?
You still need to
another
do,
points?
you need to do each point.
Yeah.
So imagine here we just calculated the vertical deformation. What happened if you needed to calculate the horizontal deformation?
And it's the horizontal vertical
You will have to redo the whole work with the horizontal force.
Oh.
But for example, if we had solved the same problem, but this time the question was to determine the vertical deformation at point B, did you need to add a virtual force? No, because you already have the force F, no? Yeah. Okay, so we could keep the force F over there. All right, so over here, let's see. What do you need?
Wasn't our force in kilonewtons?
The force in kilonewtons.
Yeah, and we never equated that.
Oh, for this 100 here,
I guess it just goes out, it doesn't matter.
I don't know.
Yeah, that's not a big deal, the process doesn't matter.
Yeah, you need to find out the process. Yeah, you need to find out about the calculation. Yes, I understand what you're saying.
And I was confused too when you said this is, how it's 45 degrees, when the triangle looks like it would be 30 degrees here and 6 degrees at the top. Because isosceles would mean it would be equal on every single side. It's not.
Okay, what should be, Matt, what should be the summation of all the angles of a rectangle? Should be what?
180 degrees.
180, okay.
And if the two sides, if the bottom is longer than the other side.
I mean, these ones are two,
Right.
right rectangle, no? So anyway, this is 45, this is 45. You agree that this angle here is going to be 45 and 45. That's the
on
only thing I did.
outside?
That's the only thing I did, no?
Okay. Yeah, it's not. This is being 50.
Okay. All right, so let's see over here now. Six, seven. All right, since we have time out of here, since I put it, so let's say additional. It was not asked on the class note, so additional stresses on each member. Okay, so this is very simple. What is the stress? The assumption that we had is that there were one force member. Okay. So let's see, if we put, if I rewrite here the table, let's say member AB, BC, AC, CD, okay, with Q equal to 0. Same table as before, I'm gonna put P here, since you mentioned that in kilonewtons, we'll have what? If we go back to that table, what was PAB? That was constant equal to 100. What was PBC? Minus 100 square root of 2. What is PAC with Q equal to 0 would be square root of 2 times 100. So 100 square root of 2. And CD will be negative 200. Okay, in the problem, it was said that all the members have the same cross-sectional area, which was 400 or millimeters square. So,
Yeah, just.
all right, so let me put 10 to the minus 6 since I forgot this one. 400, 10 to the minus 6, 410 to the minus 6, 410 to the minus 6. So then this will mean that the stress in megapascals will be 250, 353.3, 353.3, and the last one would be 500. Okay, so maybe here be careful, because if you want, you can put here the signs that you want, but what will you have? You will have, I mean, we can check that later. But we're gonna say each one of these members will be what? Tension or compression? Okay, we made the assumption that all of them were in tension, no? So the ones, really this one should be tension, this one is negative, will be compression, no? Tension and compression, no? Okay, so if you want, you can add that information. So we have about 20 minutes. Do you have the computers running or they don't run at all? Yesterday we're not working, no? So, I mean, I can do it quick, but if it's the video is recorded, oops.
Yeah.
Okay, I don't know why this is not going anywhere. Okay, so I don't know if that's one of the videos that are recorded or not. Models. PMAP. Airframe. Oh, it's not there. Okay, so, all right, so I'm gonna have to do it quick. I was hoping it was there. I was gonna tell you just watch it and do it at home, but. Okay, so in order not to run into any error, maybe what I'm gonna do here is open the FIMAP and maybe help me from the one from last semester, from last summer, so I'll go faster. All right, so let's see. Let me first create the geometry. So if I do the geometry very quick, remember we do the geometry of this one over here. So I'm going to start this. Let's say this will be 0, so I need 0, 0. And here will be 4. So let's say 0, 0, 0, 4, 0, 0. Then if I go up to this one, will be 2, 2. 2, 2. I think here 0, 2. Control A. Let's see if I do this geometry, curved lines, points. I go from here to this point, to this point, to this point, to this point. Okay, to this point. And then from this one to this one. I go a little bit faster because you are not able to open the computers, no? So you can watch the video and then slow it down. Okay, I think it's where I'm going to need help is on the next one. Materials, new. We said this was structural steel. You don't need to put anything, but I never put anything except when I'm doing class. So we say if we work in meters, 200 to the 9, Poisson ratio 0.3. Okay, now is what I'm going to need to do a bit of cheating probably. Property, new. Generally, you could use the road property, but sometimes it gives some problem. And since we don't have time to run into problems, let me use beam, element, shape, And let's see, shape. Standard. Okay, let's say it's circular bar. Okay, so let's say this is up. We know the area is what? Is 400 millimeters squared. So what should be the radius for the area to be 400? So I'm going to do here, probably I did that another semester. So FEMAP summer. Let's see, last summer, if I did it. Truss, I guess it's this one. I don't know, but let me open this one. Okay, so let's see, model, property, beam. So it looks like I did the same thing. Shape. 0.0112838. 112,838. One one two eight three eight. Is that what it was? Y going up. So let's see what would be the area. You see 400 10 to the minus 6. Okay, we have it over here, no? That was good. Okay, means up here, the Y is going up. So I know that the Y is going on the same direction as this one, and so on. All right. You see it's going over here. All right. So now let me do the meshing. Mesh control, size along curve. So let me do select all. Okay, let's do that. Do 10 elements per elements. Okay, so the problem now doing the beams, and I hope you remember that from AE 318, the FEMAP, is that you need to determine the orientation. So for this one, we'll have what? Model. So mesh geometry curve. Let's select this one and this one. Okay, it's probably gonna ask us. So here, if the tubes are oriented, I mean, you're gonna understand now what I'm saying. Maybe put one over here. This would be the correct one. All right, so if I do now this over here, you see how these tubes are being oriented, no? Okay, now mesh geometry curve. I need to do the same thing for this one. So this one, will it work or not work? Let me try to do both of them together.
No, because if you're doing a forward position, it's gonna be different.
Okay, so let's do this one together first then. So this one should be what then? What should be the orientation then? That one should be at 45 in that direction. So let's say it will be, so 1, -1. You cannot preview over here. Okay, so you did it right. Basically what I'm doing is I'm pointing a vector in that direction. Mesh geometry curve. And this one will be, I will do pointing 1 in that direction, will be then the opposite, -1 and 1. Okay. Oops, you see, it's collinear, so probably I did something bad. Mesh geometry curve.
Change your method of curve.
Wait, mesh geometry curve. Here we go. So let's see, what did I do wrong over here? So if we do here -1, okay, so now it's showing the vector and we put here 1, what would that give?
It's taking it from 0, 0, that's one. I think you have to define your base.
Okay, yeah, so, yeah, I see what you're saying. So let me cancel mesh geometry curve. So I'm not going to change it. I do it from here. It doesn't matter. So I can just do here. Yeah, but it should not change anything. And can put it here. I can do the same as before, I'm guessing. What did I do before? 1, -1?
Yeah, but I think it's defining it from your 0, 0 access point as your base, because it's a vector, right? So you have to define where it's, or starting at, your tip is its direction.
All right, so
So I think it's.
yeah, I understand what I'm saying, but I don't remember having to do that complicated. So you want to start them from the base, that's going to be at,
0, 0, so we want to start over to the other side though.
so no, we can put here then 2.
Yeah.
2, I can put -1. And then I put here 0, 1. Or
We just
1
put
over here.
one, we just put one. There, right? Yeah. It's just your base now is defined.
Okay, you see, now I did it. Okay, so tools, check, consider nodes, select all. Okay, so probably these ones should be 1, 2, 3. Yeah, 1, 2, 3 points should be common. Okay, no, smart enough. Okay, so here we go. Geometry, model, constraint, nodal. Okay, I'm not, but title. This one was simply supported. So let's see, will be what? 1, 2, 3. Can rotate about which axis can this rotate?
Z-axis.
About the z-axis. Let me do the same thing for this one. All right, model, load, nodal. I don't put titles again. This will be -100 to the 3. Cancel, so file, rebuild, yes. File, save as. Vmap summer. Let's see, summer 25. Vmap. I know I did, oh, this would be example 8, I'm guessing. So let me call this one trust, because otherwise I'm gonna have to call it trust. Run it, create new. Hopefully it's not gonna give any error. Pray. It's taking too much. Oops, I was just going for the worst. So F5. So now the problem is we're gonna have F5 deform. It said just at the beginning criteria. We could want to look at the vertical deformation. So vertical deformation should be T2. Okay, the Y. And okay, so here the problem is that what did we found? 0.11, but this will be the deformation at this point. What we're trying to find is the deformation of this point, no? So let's see, we do F5 criteria since we are close in time. If it gives us a value over here. So if we look at this member over here, what do we get? 0.01152, 0.10038, no, more or less. What do we have on the notes? What was the deformation? 12.1. All right, so let's see.
Like I said, I think it's because our units are big.
The what?
Or I think it's because we didn't do German. It should be, it's close.
No, the units are the same. I did kilonewtons, but the stuff. What happened is that, I mean,
I mean, it's
what?
close.
No, what happened here is that it's close, but it should be even closer. But why is it a bit smaller? Because this is the value, which is the average between this point and this point, no? Okay, so you should go, maybe we'll do it next time, I'll have a bit more time. Instead of finding the average value, you can find what is the maximum value at the node. Okay, but basically it's in the range, no? Does that make sense? Okay, so here we go. Let's see what I did on the one from last semester. I guess it's that one. Let's see what that one found. F5 deform criteria should be the same. Yeah, it's exactly the same, no? So basically we need to do, did I create a group? No, okay. All right, so once again, we were able to do the hand calculations and some validation with Fimap. So I know the computers were not working this week, but like again, you are not tested on the Fimap. but I highly recommend that you do these models at home, no? Okay, for practice, this is probably one of the best things you can put in your curriculum. All right, so that would be all for today. Remember that you have an exam on Thursday.